Hello everyone, and welcome back. Today I want to talk about a concept called center of mass. I'm going to go into what it means in a physics sense, how it's typically used in a first year physics course, and specifically what you need to know for the AP1 physics exam. Now, to start with the basic concept, if I have a ruler, a meter stick, since the meter stick is evenly distributed mass, the center of mass would be dead center of the meter stick. In other words, it would be the point where you could hold the meter stick up with one finger. However, with a baseball bat, you could not do that dead center. If I tried to balance the bat by putting my finger dead center, it would swivel toward one side. So, the center of mass of the baseball bat would be somewhere over here, since the baseball bat is not an evenly distributed mass, and most of the mass is on this side of the baseball bat. Now, this picture relates to single objects. And even though you may need to know in general where the center of mass is going to be, there is nothing here that you're going to need to calculate. At least until we get to a topic called torque. The more common setup that you may be dealing with this is probably the two-mass system, which I have up now. So in other words, I have a 15 kilogram physics cart at the 10 meter mark, a 35 kilogram cart at the 20 meter mark, and I can ask you, where is the center of mass of this system? Now, for the AP1 exam, and for most first-year physics courses, you don't really need to know the math. But what you do need to know is so close to the math, I'm going to show it to you anyway, because it's pretty simple, and I really believe it'll help your understanding. So what I just showed you was a two-object system on a single axis. And we're going to find the center of mass with a few different variables here. But to start out, the official center of mass symbol is this, but I've literally never seen this used in a first-year physics course or on the AP exam, so I'm going to simply use COM for the symbol. Now, here is the mathematical equation. Center of mass equals mass 1, mass 2 over mass 1 plus mass 2, and something goes in these boxes. Well, what goes in those boxes? The answer to that question is any vector. Position can go in the boxes. Displacement can go in the boxes. Velocity can go in the boxes. Acceleration can go in the boxes. Any vector that is directly related to these two masses can go in the boxes. The two most common are going to be position and velocity. So let me bring back my setup and I'll show you what I'm talking about. Here was my two-mass system. Now I'm going to take my equation up here. I'm going to find center of mass of position, which means position 1, m1, position 2, m2, over m1 plus m2. Now, before I even do this, if you look at this setup, I have 10 meters, 20 meters. Right in the middle here would be 15. If I asked you for the center of mass of the system, one thing you should be able to see pretty organically is that since I have 15 kilograms here and 35 kilograms here, my center of mass is going to be somewhere toward the larger mass. If there are 15 and 15, the center of mass will be right in between here, but it's obviously going to lean toward the more massive object. Let's check it out. 10 meters times 15 kilograms, 20 meters times 35 kilograms, over the combination of mass, which is 50 kilograms. I do this and I get the 17 meter mark, which is right about here like we predicted. Now, sometimes you can actually choose where the origin is. So what if instead of these, I made the origin right where the first card is, 0 meters, and this should therefore be 10 meters. If I did that, then I would have 0 meters times 15 kilograms plus 10 meters times 35 kilograms over 50 kilograms gives me 7 meters. So both of these are 7 meters to the right of this object. So as I was saying before, this can be done with any vector. This can be done with position, it can be done with velocity, it can be done with displacement, it can be done with acceleration. These are the most common, however, position and velocity. Now, while we're here, there's something very important that we need to discuss that actually is on the AP exam. And that is, let's say we exert a force of 20 newtons to the left on this cart only. And the question was asked, what is the acceleration of the center of mass of the system? How you do this is no different than as if this was one object. If I want the acceleration of center of mass, I'll do the net external force over the total mass. That would be negative 20 newtons over 50 kilograms, which gives me negative 0.4 meters per second squared. Now, this would not be the acceleration of mass 1. It would not be the acceleration of mass 2. It would be the acceleration of the center of mass, which we determined was somewhere around here. Now, and this is the important part, it does not matter if the 20 newtons was on this object, or if I had 17 newtons here and 3 newtons here, or I had 5 newtons here and 15 newtons here. For any of the examples I just did, this would be the exact thing you would do. they're all the same. The net force is the combination of all external forces on any of the objects divided by the total mass of the system. And for this concept, it does not matter if I have 2 objects or 20, and it does not matter if the force is on 1 object or 20. Newton's second law still holds true, but it holds true for the center of mass of the system, not the individual objects. So that means if there is no external force on the system, then acceleration, of course, would be 0, and the velocity of the center of mass of the system would remain constant. That means these objects could bump into each other all day, but if they bump into each other, they exert third law pair forces, and those forces would cancel considering they're in the system. In other words, they'd be internal forces, not external forces. So these cards can bump into each other all they want, and the acceleration of the center of mass of the system would still be 0. In other words, if they bumped into each other, the velocity of the center of mass would not change. That statement is what you definitely need to know for the AP1 exam, and you will be assessed on it. So to put it in word form, this statement is vital. If there is no external forces exerted on the system, the velocity of the center of mass of the system does not change. This is literally a restatement of Newton's first law. But if you have multiple objects, it's not the individual object you're talking about, but the center of mass of the entire system. Where this most commonly comes up is in momentum 1D collisions. They'll give you the velocity of the center of mass of the system before the collision. The 2 cars on frictionless tracks will collide, and they'll ask you, what is the velocity of the center of mass after the collision? The velocity of center of mass is the same. Unless there are external forces like friction involved, the velocity of the center of mass will not change. I'm going to end this here. I hope this helped you out. Have a good day. This is Mr. M signing off.